To me, the negative is part of the direction. Or I guess you could also do negative I hat cross j hat, so negative I hat cross j hat. All right, questions here? Similar example there. Long thin rod. Meters long. Let's give it a diameter of 0.1 meters. Axis of rotation here, we'll make this 1.5 meters. And I apply a force 4 meters away. Make this 4 meters where a force is applied of 3 newtons. And give it a mass of, what number did I not use, Jeff? 6 kilograms.
For the diameter, is that J1 or 0.1 J hat
This?
Yeah.
That's 0.1 meters. That symbol right there is an arrow.
in air?
Let's do it this way. And so the question is, what is the angular acceleration? It's going to use various things. All right, so the whole point of giving you a diameter of 0.1 meters and the fact that the length is 7 meters is that the diameter is less than 10% of the length. So it's okay to assume that it is thin enough that we can ignore it.
So is that pretty standard? So if the diameter is less than, like you said, 10% of the entire length, just ignore it?
Yeah, it's legitimate too. Now, if you're designing a building or you're designing a piece of equipment that could kill somebody, yeah, take it into account. But for Physics 151, yes, you can ignore it. I could also have just said, it's a long, thin rod, and you would just naturally have to assume that, okay, it's skinny enough that I'm going to ignore it. I know that torque. Let's actually do it by parts, like I might do on a test. That's not some strong hint, that's just the way I do my test. What's the moment of inertia of the rod about its center of mass? Assume uniform density. Moment of inertia of a rod about its center of mass. Axis normal to the 7 meters. That's also people looking it up, apparently. 4 meters. Hoping for a formula first. No. This would be on the first page. It's not something I'm taking you to memorize. It just would have been nice. So it's 1/12 times 6 times 7 squared, which is 24.5 units.
Meters.
No,
What'd you say?
Meters.
no.
If you're stopping there.
Meters rotation.
Meter squared?
Okay, you're closer.
Cube?
No, farther away.
Would it be,
Think about what you're multiplying here.
kilograms meter squared?
Yeah, kilogram meter squared. no shorthand for that.
How do we get that, the meter squared, even though the whole thing is 7 meters?
We're squaring the 7 meters. Is that, your question is how do we get meters squared?
No, yeah, I got that, but
Okay,
like,
sorry.
how does that fit in? Cause if the whole thing's 7 meters, how is it 24.5? Like,
It almost sounds like you're asking me how did we get the 1/12 ml squared? I mean, this was a plug and chug.
Yeah.
From what you have the formula. The formula requires calculus, really.
huh,
I assume you don't want that right now.
no.
Especially as I'm trying to remember how,
You're fine. It's okay. I'll figure it out later.
okay. When you take calculus, that would be Calc 2. So first day of Calc 2, you should just say, hey, moment of inertia of a long thin rod about its center of mass normal to the length, go, and have him do it, or her. All right. What's the moment of inertia of a rod about the axis of rotation?
Is it the same equation?
It is not the same equation. It's a question of how do you actually get it when the axis of rotation is not at the center of mass? Besides deriving it from scratch.
1/3 ml cubed.
Suddenly you're gonna change units on us to kilogram meters cubed?
1/3 ml squared.
That would be about the end. This is about some point in between the middle and the end.
Would you do the L would be the 4 meters. Do you have to apply the force that's being pushed on?
The force is irrelevant to this axis, to the moment of inertia.
1/6 ml.
All right, instead of just calling out random numbers, parallel axis theorem, anyone? We did talk about parallel axis theorem, right? Judging from Ali's comments that he sees in his notes.
Plus, so it's gonna be 1/2 ml squared.
Or
Plus
1/12 ml squared.
1/12 ml squared. Plus mh squared.
All right. Parallel axis theorem, the moment of inertia about some point P is equal to the moment of inertia about the center of mass plus mh squared, where h is distance from center of mass to point P.
What is this again?
Parallel axis theorem. I guess PAT for short. So, it's going to be the 1/12 ml squared, which we already have a number for, but what the heck, let's keep letters in. Plus m 4 squared. Because we've moved the axis from, oh, wait, no, sorry, not 4. The center of mass is here, a distance of 3.5 meters. And we move it towards 1.5 meters from the end, so we're moving the axis 2 meters. So 2 squared. 24.5 plus 6 times 2 squared, which is 24. 48.5 kilogram meter squared. questions to hear.
Is that for the IROD axis of rotation?
AOR, axis of rotation, yes. So it's the moment of inertia of the rod about the axis of rotation.
So to get the 2, we just did 3.5 because the whole thing is 7 meters minus the 1.5?
Yes, yeah. If you had gone for 4 meters, as I originally did, there would be a deduction for that, but not as big a deduction if you just skip the parallel axis there altogether. Sorry, flashing back, I've had parallel axis, I've had shifting of the axes on several tests in the past, and just students often forget it. They give me the same answer for both.
Oh, for both the,
About the center of mass and
the angle of rotation.
axis rotation. All right, so next step, what's the torque about the axis of rotation? Well, we've already done that. The torque is negative 12 Newton meters K hat. And the last step, what's the angular acceleration? Well, I know that torque is equal to I alpha. And so negative 12 Newton meters K hat equals 48.5 kilogram meter squared times alpha. And so we end up with alpha equal negative 12 over 48.5 K hat Newton meters per kilogram meter squared. Yeah. All right, so anyway, that's the math piece right there. What does that equal? Let's just be just shy of 0.25.
Am I wrong in remembering that Newton meters is joules?
Hold that thought, we're gonna come right back to it. It is not joules here. We'll get back, but that was a point I was hoping to make at some point.
0.247.
Put a little gap there for the units, K hat. All right, so let's talk about units for a moment. A Newton meter is a joule if you're talking about energy and work. A Newton meter is not a joule if you're talking about torque. It is unfortunate, but that's just the way it is. Do not put joules when you're talking about torque.
Why?
Because the powers that be made it so. Because when you break down joules, the educated physicist is gonna go, oh, all right, he's talking about energy and work. And if you suddenly call it torque, they're gonna be confused.
I have a question. So
Yes.
when you multiply negative by positive,
You get a negative.
yes. So does that not matter in this case?
Oh, it does. I had the negative there, I forgot to do it here.
Okay.
Thank you. All right, so what are the final units? Because Newton meters per kilogram meter squared is awkward. We want to streamline that.
Newton meters squared?
No.
Newton meters kilograms?
All right, so what I'm hearing, it sounds like from almost both of you, if I did 4 divided by 4 squared, I would get 64. Just say
That's not how
no.
math works.
Yeah, that is not how math works. If I got meters on top and meters squared on the bottom, what happens there?
One of them cancels out.
Yeah.
So it'd be newtons over kilogram?
Okay, now we can take it one step further. What's a Newton divided by a kilogram meter?
A new,
A Newton kilogram meter.
Not how math works. What's a Newton in its base form?
A unit of force.
What's the definition of a Newton? Take F equals ma. A Newton is
Force.
a unit of force, it is not force itself. What are the units of mass?
kilograms,
Units of acceleration?
meters,
Per second squared.
square.
Okay. So a Newton is, by definition, a kilogram meter per second squared. So over there, I've got a kilogram, a Newton over a kilogram meter, and a Newton is this. So I have a kilogram meter per second squared divided by kilogram meter.
So you're just left with
Second squared.
second squared.
Newton second squared.
Yeah, you stepped out of ballpark.
1/2 squared.
Remove the question mark.
1/2 squared.
Yes, 1/2 squared. Because remember, anything is, can be turned into a fraction. Fractions are just division, so it's a kilogram meter per second squared times divided by a fraction, so just multiplied by the reciprocal, 1/kilogram meters. I'm left with 1/2 squared. However, we're talking about angular acceleration here.
So it has to be, there has to be meters somewhere in there.
No,
No.
angular acceleration.
Is it radians? Is it radians? Or no?
Per second squared, yeah. Radians per second squared. Now, if you wrote 1/2 squared, it's not technically wrong. However, radians per second squared, it, to me, is clear communication of what's going on. All right. Questions to this before we make it more difficult? Not more difficult. Before we add forces, we add stuff. All right, let's add stuff. We'll keep it 7 meters long. A mass equals length. Mass is 4 kilograms. I guess I made it 6 before. Let's keep it the same. So 6 kilograms. We're gonna make this distance here 2 meters. That distance there 1 meter. This beam is in static equilibrium. What is the tension in each rope? Now before, if this were a chapter 4 problem, I would have to give you the tension in one of the ropes for you to figure out the tension in the other rope, but we can now be more sophisticated. So we're gonna start out with everyone's favorite, force diagram. Facades has not gone away. All right. What are the forces acting on the beam?
Two pulling forces from both ropes that are going up, I guess.
Yeah, all right, so I got it. We're gonna call it tension 1 and tension 2. Actually, I'm gonna simplify that. I'm gonna make this, this one A and this one B. All right? So we're looking at F, Tom,
And then
tensions.
weight pulling down.
Where?
Right in the middle.
As far as we're concerned, yep. Uniform density, I didn't mention that before. If you get into civil engineering, at that point, you'll take into account the fact that the weight is distributed across the whole thing and not just concentrated at the center. But if you're not doing that, in the middle is good enough.
And I would think it's in the middle just because you said it was in equilibrium. But I guess that doesn't really make sense.
That could be off-centered. All right, what about FON?
There's no friction. There's no God force, or outside force. And then there's nothing serious touching it.
All right. The only thing that's touching are the ropes, and the ropes accounted for as tension. All right, so, equations of motion. Oh, I guess coordinate axes. No, acceleration. We got the force diagram. What's the direction of acceleration?
Nowhere.
Okay, so we can choose whatever we want. I recommend up or down to be positive. Pick one.
Up.
That is sad and pathetic arrow. There we go. All right. Coordinate axes, we just did. Decomposition, do we need to break any of this up?
No.
Okay. Equations of motion.
A plus B